Atwood machine. You see these commonly, you see them all over the place, as long as you're looking inside physics textbooks. There's a mass here experiencing gravity up to this frictionless pulley, and it's pulling this second 40 kilogram mass on this frictionless table, probably made of ice. And so this is M1 at the top. This is M2 here. Now what's great about this system, they're connected by a string, or I don't know, frictionless rope, massless rope. Force of tension is the same in both cases. The acceleration, the magnitude of the acceleration is the same in both cases. What a pulley miraculously does is change the direction of the force. And so just to keep things simple, if this system is moving, if it's moving down here, it's moving to the right there. And so we are going to say, for convenience sake, that down is the positive x direction. Now the second thing that's significant, and I think I already mentioned it, the force of tension is the same in the strings, but they're also accelerating at exactly the same rate. So acceleration is the same for these two bodies. Okay, so M1 times A, we're not going to worry because this is the components that are perpendicular to the surface are canceling out. The force of gravity and the normal force are going to balance out to zero. So the first mass times whatever the acceleration is going to be equal to the force of tension. Okay? Now, this mass is also going to be accelerating at exactly the same rate. It's experiencing two forces, and so the force of gravity minus the force of tension, because we've decided that the force of gravity is down, and so this is mass times acceleration is 9.8 meters per second squared times m2 minus the force of tension. Okay. Now, there's a little trick when they do these. What they do actually, I think it's almost a little bit silly, but you add 1 and 2 together. And so m1 times the acceleration plus m2 times the acceleration is equal to 9.8 times mass 2 plus the force of tension minus the force of tension. And so the forces of tension actually cancel out. Okay. Now, unfortunately, this tension thing sort of convolutes the problem, because really this is just saying the force is equal to the total mass of the system times the acceleration. So it's convoluted the problem a little bit, but if we want to work out the acceleration, we can actually factor it out of this, m1 plus m2, and that's equal to 9.8. Hope my points are big enough, times m2, and then to fix this all up so we can isolate acceleration, we're going to divide both sides by m1 plus m2. And this is just saying the force on the system divided by the mass is equal to the acceleration. And so there's a good way of doing this where you don't do this whole deal with tension. It's just F equals ma. Anyways, we could calculate this, but I think I'll leave that to you guys.